Welcome to part 9 of a lecture on catalytic organometallics. In the preceding lecture, we already had an example where a vinyl halide with an internal olefin reacts in a palladium catalyzed process. Oxidative addition again to the carbon-bromide bond, carbopalladation of that olefin proceeds, of course, with a ring closure reaction, beta hydride elimination, then could in principle deliver a diene which you can then apply in Diels-Alder reactions. However, initially the hydrido-palladium halide as an electrophile is still coordinated to that olefinic moiety and can re-add again a hydropalladation with the eta-1 allyl complex first, and in equilibrium then the eta-3 complex is formed. And now imagine that the substituent R is a side chain with a nucleophilic center could be a tosylated amino group which becomes, of course, acidic, and in the basic reaction conditions which are typical for a Heck reaction, it can be deprotonated in equilibrium. So that we have an internal nucleophile which can attack that allyl palladium complex in that case the reaction would result in the formation of this heterocyclic system, that palladium bromide, an 8 complex, would be set free. While on the first glimpse this looks a bit odd, however, you must imagine we have, of course, additional ligands. So, and here you see it's just a palladium 0 complex which is further activated by a coordinated bromide. Well, obviously, you can use allylic palladium complexes, pi-allyl palladium complex, for attacking with nucleophiles. Let's have a look at another interesting example. a carbamate functionality here. A highly functionalized system. The palladium catalyzed reaction was studied with this substrate in context with the synthesis of morphine alkaloids. Palladium 0 catalyst, relatively high loading, base, and a 56% yield was obtained. Well, the structure, maybe you should try to figure it out by yourself. Some hints for solving the problem. The palladium will react with that carbon iodide bond, of course. So a carbopalladation will take place, well, at that diene system. And the allyl palladium halide will be trapped by an internal nucleophile, and guess which center will be the nucleophile. Okay, we are under basic reaction conditions. What is the most acidic position? And then you have it. Okay, please have a try. One additional hint, you have some cyclohexane or aza cyclohexane moieties, and it helps if you draw that in well, chair conformation. So it's clear that the palladium will insert into this bond here, and then the intermolecular Hack type process, the carbopalladation, will take place at that double bond, connecting this position and this one. This is a 6-membered carbon chain. Okay, so how to draw that? Well, I must admit this is a bit tricky. You have 2 annihilated cyclohexene moieties. Now this substituent placed in axial position then it's not a problem to draw a connection to the center. So 56%. So, and here we have the allyl palladium complex. Well, what will happen next? This phenol unit is deprotonated and acts as an internal nucleophile. well, actually this center is a bit far away. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. Well, 7-membered ring formation in or the 5-membered ring formation. As I said, this is a rather rigid system, and therefore, while it can't reach until this position, the 5-membered ring formation will win. And let's draw the final result. That's it. Well, palladium 0 and hydrogen iodide. Hydrogen iodide, of course, trapped by the base. 56% yield of a rather complicated framework, typical for some morphine alkaloids. Imagine the following reaction. We have this allyl acetate at the cyclohexane moiety. Trans stereochemistry, well, this is a chiral system. And we add a nucleophile, in this case a soft nucleophile, a malonate. What about the nucleophilic substitution? Well, where in principle a lot of stereoisomers can be formed, this would be an SN2 prime where the malonate is introduced into the molecule from the same side as the leaving group is located. Well, to make it clear. Does this reaction happen if you put those reagents together? No. The acetate is not a very good leaving group. Well, if you would heat that up, somewhere it would react, of course, and especially in rather polar solvents. However, under palladium 0 catalysis, this reaction works very well, and it is a name reaction. It's called the Tsuji-Trost reaction, or the Tsuji-Trost allylic substitution. Invented independently, Trost started with allylic acetates and Suji with allylic carbonates, but essentially it's the same reaction. How does that work? all in detail. Palladium 0 reacts as a nucleophile, and in an SN2 or SN2 prime reaction, the acetate is substituted. The palladium generally attacks from the opposite side. So the substitution under inversion. Okay. And in this case, well, first an eta-1 palladium complex might be formed, and this isomerizes to an eta-3 pi-allyl palladium complex. The acetate will coordinate to the palladium then. Like that. Then that soft nucleophile will attack, and usually the soft nucleophiles attack, well, again under inversion. That means that the net reaction is under retention. Hard nucleophiles prefer to coordinate to the palladium, and then a reductive elimination will form the bond, let's see, for instance, the carbon-carbon bond or the carbon-hetero bond from the same side as the palladium was located. But these soft nucleophiles attack from the opposite side, and that means we would get this product, and unless we have suitable chiral ligands at the palladium, we will get a racemic mixture of these two products. Of course, it would be interesting if this Tsuji-Trost reaction could be done under enantioselective induction. Well, but imagine having a ligand here at the palladium. How should that ligand influence the approach of the nucleophile from the other side of the ring? A difficult problem, but it has been solved in the 90s. In most cases, bidentate phosphor-nitrogen ligands are involved, which are then, of course, chiral. Let's have a look at one of those examples. In those cases, you could use those chiral allylic acetates. Well, they are chiral but racemic. It doesn't matter, because the intermediary palladium complex, if no chiral ligand is at the palladium, is of course achiral. So, and now we need that soft nucleophile, the palladium catalyst, the palladium 0 catalyst, and a ligand coordinated to the palladium. And the typical one is, for instance, this chiral oxazolene ligand. Or made by chiral pool synthesis, initially starting with the corresponding amino acid valine in this case. Let's have a look at the intermediary palladium complex. So, I try to draw that. Phenyl group. Allylic system. Allyl palladium complex. The acetate might be coordinated at the palladium, or should be coordinated at the palladium, but could also be non-coordinating anions present. So, the palladium chelated and of course a lot of steric interaction of those phenyl groups with that allyl substituent, the isopropyl group here. As a net result of steric and electronic effects, some kind of trans effect. The nitrogen has more influence on the trans carbon, and also with phosphor on the other one. Well, steric interaction is also responsible for the fact that that allylic system will not be completely symmetrically coordinated to the palladium. At the net result, we will have somewhat difference in electron density between that carbon and that carbon. And therefore, one attack will be preferred, and as worked out by Günther Helmchen's group at Heidelberg University, and I think also a Pfalz group. In this case, the nucleophilic attack is preferred at this position, and finally, this enantiomer is formed as the preferred product with up to 99% enantiomeric excess. Very impressive, I think. A special case of the Tsuji-Trost reaction is an example which is connected with the so-called TMM chemistry. Trimethylene methane. Imagine this with 1,3 dipole or with diradical. Wow. You might try to start from something like that, but you have to activate then 1 C bond to break it homogeneously or heterogeneously. But one method that has been developed also in Tsuji-Trost's group is starting from an allylic acetate having a TMS group present in close proximity. And this, under Palladium catalysis, is a synthesis equivalent for this, well, you would call it synthon in retrosynthesis planning. Okay? Well, with Palladium 0 catalysis, you certainly then have this intermediate, and this will react, although some details might be somewhat unclear, with functionalized olefins, especially with alpha beta unsaturated carbonyl compounds, resulting in cyclopentane formation, those with that exocyclic bond. One recent example from a natural product synthesis with ester was used palladium acetate, a phosphide as ligand, resulting in the formation of this product 87% isolated yield. Of course, you don't need chiral ligand in this case because you already have the chiral information within your substrate. Finally, for today, let's go through the synthesis also of a natural product. It's called allosamidsulin. It is an inhibitor of chitinase, and its structure is this one. Cyclopentane ring, highly functionalized. So, synthesis was done in the Trost group by David van Ranken. I was lucky to witnessing that synthesis in the lab of Barry Trost at Stanford. David van Ranken now is a professor at the UC Irvine. Well, and this is indeed an intriguing synthesis with very few steps and an overall yield of 25%. This becomes important soon, as you will see. Well, the cheapest substrate to start a synthesis of cyclopentane functionalized cyclopentanes certainly is cyclopentadiene. Of course, you start with the dialzaldodimer. You crack it, and then you have the cyclopentadiene. Putting in functionality, well, treatment with a base and introducing an essentially this side chain, the hydroxymethyl group, but for the synthesis protected as a benzyl ether. So, a base and chloromethyl methoxy, right? I'm not completely right, this name. So this was the reagent. Chloromethoxymethylbenzene, yes, okay. If you choose the right base and the right reaction conditions, you will get the diene system not in conjugation with the additional substituent. Now, you need singlet oxygen. You can produce photochemically with an activator. You use rose Bengal. So, and in addition, well, you form an endoperoxide and you want to reduce the oxygen-oxygen bond of that endoperoxide, and with thiourea you have a mild reducing agent. So, the Diels-Alder reaction with a singlet oxygen will take place, of course, opposite to this side chain. Or maybe I should draw that first. It becomes more clear. So this is the endoperoxide and then you have to reduce that bond. Resulting in this, well, diol, both hydroxyl functionalities in allylic position. So going on with this synthesis, I will change the blackboard to the next one. Two equivalents of a tosyl isocyanate are added, and as you know, isocyanates with alcohols form carbamates. So a double carbamate formation should occur certainly the carbamate is a better leaving group than the hydroxyl group itself. And indeed, it's good enough as leaving group that it can be activated by a Palladium 0 catalyst. So it is already now suited for a Tsuji-Trost reaction. Well, this reaction was done while the real nice chiral catalysts weren't present at that time. It was in 1988, and well, you don't have a selectivity, a chiral selectivity now for the Tsuji-Trost reaction in that case. What will happen is that one of those carbamates are substituted So, the allyl palladium complex is formed under the basic reaction conditions that tosylate will be deprotonated and the nitrogen nucleophile will then substitute the palladium. So, let's go back to this blackboard. In the paper by Trost and van Ranken was reported that the synthesis of this intermediary product starting from the cyclopentane was achieved in, well, not a very good yield, just 33%. And remember, the overall yield of a process is 25%. So we should not lose more material, far more material during the next steps of the synthesis. And indeed, with double carbamate formation and the Tsuji-Trost reaction worked out with a 93% overall yield. Just two more steps. Standard procedures. Transform this heterocyclic moiety to the target one. This one, well, one could look that up, how it was done under reducing conditions with sodium and naphthalene. You get rid of the tosyl functionality. You have the NH here then, works with rather good yield. Then you have to perform an O alkylation with trifluoromethane, sulfonic acid, methyl ester, and then just with dimethylamine as the nucleophile make the exchange, and you are at this stage of the whole process. So, what has to be done now? Well, later on, as the final step in the synthesis, you can remove that protecting group by simply hydrogenating it with palladium and charcoal. But we have to introduce two hydroxyl groups. Well, one here with the OH group behind the blackboard, and the other one with the OH group here on that side. Van Ranken had to focus on how to get to this peroxide well, you might say simply, well, epoxidation with per acid. Well, that's not that easy. Remember, this is a roof-like molecule, and the epoxidation has to proceed endo, but it doesn't want to, of course. So, well, initial tests didn't work. You get mainly, by far mainly, the epoxidation from the exo phase, and now it was the idea, well, one should trigger the steric demand of that protecting group, make it bigger by a host-guest interaction. Besides the peroxide, cyclodextrin was added. Cyclodextrins are cyclic sugar molecules with a lipophilic cavity. And host-guest interaction, well, this a non-polar side chain goes into the cavity. That huge cyclodextrin molecule is sitting on the roof and preventing the epoxidation from the exophase. And this is enough for, well, achieving the epoxidation from the endophase. Well, problem is almost solved then, a few more steps, and after a lot of work, David van Ranken succeeded in finishing this synthesis. Well, end of this lecture. Some greetings to David at the UC Irvine. I noticed last week that he also has some nice organic chemistry videos on YouTube. Well, thank you for listening. See you next week.